All right. Good morning to everyone, or good evening to some of you, and welcome to the first AI4Life Talks. My name is Zhang Yuan, and I'll be your host today. And it's a real privilege to welcome you to this series. AI4Life was created as a community for life science researchers to share ideas, knowledge, and experience around cutting-edge AI technologies. The innovation talks are designed to be short, focused session where tool builders like yourself and researcher explain how the model works, where they can be useful, and what are the limitations that matters, and more importantly, how they fit into real research workflows. Think of this as just a practical forum to explore tools that can help drive your work forward. Today, it's my absolute pleasure to introduce our speaker, Dr. Yunchao Liu, or Lens. Dr. Lens Liu is a scientist at A-Star Singapore, specialized in AI for drug discovery, with expertise in geometric deep learning, genomics, and small molecule therapeutics. He's the author of SuperWater model and the paper SuperWater as a generative AI framework to predict water molecule position on protein structures. And that is going to be our focus for today's session. And I hope it will spark ideas relevant to your own research. Our agenda today includes a presentation from Dr. Leslie on SuperWater, covering the relevance of the model, how to use it, and a demo on background later. We'll then move to Q&A session with questions submitted by the audience. If time allows, live discussions. With that, I am very excited to hand the floor to Lens to take us into the frontier of generative biochemistry. Please.
Thank you, Dan, for the kind introduction. So hello, everyone. I'm Yunchao Liu and also go by Lens. So I'm a computer scientist by training, and today I will talk about SuperWater. Let's dive into the first slide. So why water molecules are important? As we all know, most biological processes, they occur in aqueous environment, whether you're studying RNA, protein, or membranes, you always have water surround it. And also, water is very important because it can strongly influence the structure. Like this is a GPCR structure. You can see there are a lot of water molecules mediating the interaction. And a lot of us are like designing drugs. We can also see from here, water molecules are also very important in the binding pocket. In this illustration, you can see like this is a small ligand binding to a pocket with a water network inside. But in this experiment, the author, they mutate this protein from the wild type to this mutated one. I'm not sure if you can see my cursor, but you can see on the right-hand side, the image, the author mutated one residue, then the water network got unhappy. So this binding affinity leads to 1,000-fold decrease in this binding affinity. So you can see the water network also has great impact in binding drug design. And let me go to the next slide. Sorry, the slide is a bit slow. Yeah. And also, as we all know, that binding energy, there's an equation. We always try to calculate the binding free energy. And most of the time, people just try to calculate the delta E for the ligand for the protein. But in the real world, water also matters. But because it's kind of complicated, a lot of time it's ignored. So then in the actual binding free energy calculation, you also need to know the delta E, the first term in the red square here. The ligand water basically means like the ligand need to break the water network, break hydrogen bound, then go into the protein. The protein also need to break the water network, break the hydrogen bound. Then the water network within them, they also need to break those hydrogen bonds. These are also associated with the energy changes, and also see the last term in the red circle, also this entropy. The water that was happy inside of the pocket now need to be released into the bulk water. So these will also cause some entropy change. If the water was very like constrained in the pocket and released into a more free environment in the bulk water, then the entropy will increase. And this, because this is a minus term, then the total free energy will very likely go down. So that's the very strong drive for the binding of the ligand. And the next slide. Yeah, but even though it's so important, there are a lot of times because of the computational cost, water are modeled implicitly, as you can see in the first row here. So they basically treat the water as a continuous solvent medium. It may be less accurate, but because it's a simpler method, so it costs less computational power. And also, if we want to be more accurate, we can explicitly model the water molecule as like each atom. Yeah, as you can see, there are two illustrations down the table. On the left is the explicit solvent. You can see all the red dots are the water explicitly represented. On the right is the implicit solvent. Basically, just use some parameter to represent the water. Yeah, so you can see it's basically a trade-off between the accuracy and the computational cost. Then the question we ask is that whether we can model the water molecule with better accuracy and also lower the computational cost in the era of AI, use the AI to help us do this. So that's the main motivation of the SuperWater. And we can also see some current methods. The first row shows some more traditional ones, use some physics-based modeling methods. It's very time-consuming, so it may take days to run your model. And then there are also some knowledge-based, Monte Carlo-based methods. Then it goes to like AI-based model, like the Galaxy Water CNN, hydroprods here. They are like some AI-based model. They use the CNN for calculating that. Then our work, SuperWater, we use diffusion model. Diffusion model is also a kind of AI model, and it runs much faster. And later I will show you more what diffusion model is. Yeah. So first, in order to train the AI model, we need to prepare the data. So here are the selection criteria for our model. So we chose ratio number between 100 to 500, and also because we want like a very good structure, so we choose a resolution better than 1.5 angstrom. And there should be enough water in the structure for us to actually train the model. So the ratio of this water to residue number is set to 0.6. So basically, we need to have more water, for the model to be trained. And for the training data, it doesn't only contains protein. They also have protein-protein complexes, and also protein ligand, protein ion, and protein nucleic acids. Yeah, and we chose water around the protein surface within 4 angstrom, because this basically is where the hydration shell is. And here we split our data into training set, validation set, and the testing sets. And we use in the computer science field, there is a set model called this score-based diffusion model. So we basically use that model to train our model. Yeah, and I will talk more about what score-based diffusion model is later. Yeah. And in our model, each water molecule is treated as a single point, basically owning the oxygen, so we don't have the hydrogen there. And here's the overview of the SuperWater workflow. So first, we use this, you can see step 1 here, use a generative diffusion model to predict something called a score. And I will explain more what score is later. And on the right-hand side, you can see how those data are actually represented in the model. First, water molecules are inputted as a graph. So in computer science, graph is defined as a set of nodes and a set of edges. So yeah, water molecules are basically it's a water graph, and also protein is also defined as a graph. And there is also a cross graph that try to capture the interactions between the water and the protein. So we have these three graphs that captures water-water interaction, protein residue interaction, and the water-protein residue interactions. And we use this updated feature. Basically, it's something called a graph neural network to learn all these interactions between different nodes. Yeah. And this is a SE3 equivariant neural network. But SE3 basically means that it's rotation and the translation in equivariant. Yeah. And once we have this output, it will give you predicted water molecule positions. Then we use a confidence model to basically help you filter the predicted water molecule. If a confidence model thinks this confidence for this prediction is too low, it may filter it out. And then in step 4, we use a cluster algorithm to cluster some water predicted molecules that are very close to each other, cluster them into one. That gives us the step 5, the final water positions. Yeah, so here's some more details about the diffusion model. So yeah, you can see on the top left, this is the input. This is the structure, the protein with the actual water position. And in the fourth, on the top here it says forward SDE. SDE stands for stochastic stochastic diffusion. Differential equation. So basically from the water original position, we will add more and more noise. You can see here data to noise. So the data will be totally perturbed into a normal distribution. So the water will randomly be disturbed. So this is basically what a stochastic differential equation tells you, how to move from one location randomly into the normal distribution. Then in statistics, basically people have studied, they have a way to restore the signal from the noise, from the random noise. This is called a reverse, using this reverse statistical differential equation to go from noise to data. The key here is to know something called a score function. The score function basically is like a map guide, tells you where your data point should go in the probability landscape. It always points to the direction where the probability is higher. So the data points once we know this score function, you can imagine if we have a water scattered randomly in the space, this score function will tell you where to go. You can get a higher probability. So by using this score-based function, we can gradually move the initial water position from a random place gradually to the place where it has a high probability. Yeah. So this score function then is the key part where the AI model needs to learn. So by using the training data, it will compare the predicted score function with the actual score function. So the AI model actually is learning this score, where to go, in the probability landscape. So in the end, the output actually is the water position with the higher probability. Here is also another illustration. You can see from like a normal distribution, those waters gradually it will converge. It will go into like a more possible position. All these water molecules. Then we use the confidence model to filter out all the waters that are of a low confidence. And in the arrow in the very bottom here, we then use the clustering algorithm to cluster close water into one. And you can see then it compares with brown juice. You can see in the beginning on the top right, lots of predicted water. And using the confidence model, you can see it then filter out a lot of unlikely ones or the ones with low confidence. Then, on the bottom left side, you can see with this final water position, it's more close to the ground truth in the middle. And here is also like some results comparing with other AI-based models. Yeah, because these two models in their respective paper, they already compared their methods with the previous methods, and they show they are better than the previous method. That's why we only show our comparison with these two methods. So you can see this is a precision coverage plot. Coverage basically is recall. Precision basically is telling you within your prediction how many of them are the actual true prediction. Coverage basically is within all the true water molecule positions, how many of them you can recover them. Yeah. So this curve basically more towards the top right, the better the model is, and the different points of in the curve basically represents different confidence cap. You can see, for example, in the cap 0.5 here, that means you have a very high confidence threshold. And if you move along the curve to the right, then the cap becomes smaller and smaller. Like the lowest one we have is the cap 0.02. Because if you lower the cap, the threshold, basically you will have lower precision because the model is less likely to give a prediction because the threshold is when the threshold is very high, then it will give like a very a good precision because it will only give the very confident one. And you can see the SuperWater in general is better than this the orange line, the hydroplot one. Yeah, and the hydroplot, as you can see, is thoroughly better than the green line, the Galaxy CNN one. So yeah, we show on these two scenario. One is a protein-protein interaction, one is a protein-ligand interaction. We can see the general performance of this SuperWater and the two other AI methods. And we will also see some very specific examples and some visualization to show you how it actually performs. Go to the next slide. Yeah, here, this is just a protein by itself. You can see here the red ones are the experimental, the actual ground truth water molecules, and the cyan color is what the SuperWater predicts. And hydroplot is the yellow color. We don't show the Galaxy one because hydroplot is already better than the Galaxy water. And also, if we plot too many things on this image, it will look very messy. That's why we only show SuperWater comparing with the hydroplot. And here we have two zoomed in highlight details. You can see here on the left one, hydroplot has a lot of false positive. Basically, it predicts some water molecules that doesn't show as the ground truth. In the meanwhile, the SuperWater, actually, you can see they correspond pretty closely to the actual ground truth, the red one. Basically, the cyan and the red color, they are very close to each other. While the yellow color, you can see they are quite scattered, a bit far away from the red color. And this is for the protein just by itself. And we can also look at protein ligand interactions. Yeah, because it's very important for drug discovery. In this example, you can see there are some water bridges. Yeah, and you can see also these three interaction places. They are labeled as position 1, position 2, and position 3. So even though hydroplot also captured some positions in position 2 and position 3, but it missed the position 1 interaction. Yeah, so you can see, yeah, in position 1, basically there's no yellow color there. And here also another example for the protein-protein interface. So yeah, here you can see two protein, they interact with each other. So they are in the ground truth, there are actually 12 water molecules there in the interface, but the hydroplot only recovered 8 of them. So in the two detailed zoomed image here, the right hand side, you can see most of the time it doesn't even have the yellow color. Only one yellow color is visible. All the other ones are missing. Yeah, but SuperWater, it can recover 11 out of the 12 water molecules in this interface. And yeah, that's basically the introduction of the SuperWater. Yeah, and I guess now I should go into the live demo. So we will now look at a live demo here. So on this page, this is the PDB structure we are going to look at. We are going to look at this 1HEW structure, which is hem egg white lysozyme. So this is an enzyme that breaks down the bacteria cell wall, and this is a classical example to look at because this structure was deposited into PDB around 1960 or so, and it is a pretty standard benchmark. It also has shown the importance of the water interaction. And more importantly, this structure is not in the training set because our training set contains structure less than 1.5 angstrom resolution, and this one is bigger than that, so it is not included in the training data. So yeah, so this is a structure. Basically, this enzyme will bind to the hexosaccharide on the bacteria cell wall, and in those cubes are the monosaccharide. So here, this is basically a trisaccharide, not a hexosaccharide, because scientists, they try to use those trisaccharide to examine the mechanism of this breakdown of the bacteria cell wall. Because if they use the hexosaccharide, it will be breakdown immediately, so they cannot analyze the interactions. So they use the trisaccharide, and they can look at the interaction. Now, specifically, let's focus on the interaction. So we will click on this first saccharide here, monosaccharide here. Yeah, as you can see, so here there are a few water that are very important. So like this one is one water bridge. Yeah, so it has interaction with both small ligand, the ligand here, and also this residue here, and also these two water molecules. Yeah, now let's look at the predicted results. So I have ran this prediction on the Vecura platform, and I've ran it with two sets of parameters. So on the left side, this is the input, and on the right side, this is the output. And we can first take a look at the input. So yeah, this is basically the structure without the water molecule. You don't see those red dots. So this is the structure. I use the Chimera to get rid of all the water molecule as our input. And for this parameter set, I use a higher confidence cap and smaller initial water molecules. And for this parameter set, I use a smaller confidence cap and more starting molecules. So basically, this one with smaller confidence cap and more starting molecules will give us more final water molecules, while this one with a higher confidence cap, less threshold, only those with high confidence will be capped. So it gives fewer water molecule predictions as you compare with these two. So first, let's look at the one with a higher confidence cap. So yeah, so we can zoom in here, look at the interactions around here. Let's see. So yeah, as you can see here, there is also one water bridging this residue with this first monosaccharide here. If we compare this structure with the brown juice, so this water is the one corresponding to this one. But as you can also see here, the other two water, this one and this one, this one and this one, they are missing in this prediction because we've set the confidence cap threshold really high. So if the model is not meeting the confidence cap of predicted water, doesn't meet that confidence cap, that will be filtered out. So that's why we don't see these two water molecules. In this parameter set, if we zoom in here, uh, zoom in here, yeah, we can see here one water molecule is predicted, which also corresponded to the left one here, this left one here, and this water molecule. See, this one corresponds to this one on the right. So even though you don't directly see the hydrogen bound for the third one, but you could clearly see there is another water molecule predicted here, even though it's not perfectly aligned. Yeah, but you could see there is another water molecule near the ground truth. So yeah, so this just highlights the importance of the confidence cap. So if you only want to look at those predictions with a high confidence and you don't want a lot of false positive, then you should set this confidence cap to be high. But if you want to look at some very evasive water molecules, then you want to set a confidence threshold to be low so you can capture most of the predictions. Yeah, so that's the demo for today. Thank you.
Thank you, Lens, for the very super insightful presentation and demo. This is Lynn's contact. If you have any question, you will also, I guess, also reach out. But now we move to sound into the Q&A portion of today's session. We have received several questions before today's meeting. I'm just gonna read them out for Lynn's to address. And after that, if time allows, we will be open for live questions. But feel free to drop the question in the box in the chat, and we'll come back to that. Okay, so the first question is, in which aspect is SuperWater most different from traditional placement tools like Waterdog?
Yeah. So Waterdog essentially uses AutoDock, basically treats water as a ligand and try to use the docking program to predict where the water is. So it basically treats each water individually without considering the water-water network, their interactions. But like SuperWater, because the whole water is input as a graph, so their interactions is intrinsically considered. And also, like a Waterdog, it has some predefined functional group. They have 11 polar functional groups defined. So it's kind of it's kind of empirical and it tells you whether water molecule is. So if your structure doesn't contain those 11 functional group outside of this knowledge base, then you will have very poor performance. But like for the SuperWater, because it actually tries to learn the actual interactions between different atoms, between different chemical components, so it can predict in different environments where the water should go.
Yeah, so I think that's that highlight of intrinsically capture the characteristic of water and those interaction is very, very important in this piece. Okay, so then we know how super water is different, but why is creating water placement so critical for drug discovery? Maybe we can also give some example for some of the audience here. That'd be great.
Yeah. So as we also show in the introduction slides, why water is important. If you remember the happy phase and the unhappy phase. So basically, yeah, the water. So basically around protein or ligand, not all water are equal. Some waters, they are very free in the bulk water, but if they are trapped inside of the pocket, its freedom is constrained. So it will be very unhappy. So once that this water released into the bulk water, the entropy will increase. So it will be happier. So then the designing of the drug for the binding actually is try to use the ligand, try to kick out those unhappy water, release them into the bulk water to make them happy. That's one aspect. The other aspect is also about the water. They will form those bridges that will strengthen the binding. So as we show in the demo, yeah.
Well, thank you for the answer. So, you say super water is protein only. What does it mean for hollow structure? Perhaps with a bow line.
Yeah. So it's not just protein only as we've seen in the slides. In the training, we already included the protein-protein interaction, protein ligand, and protein ion, protein nucleic acids. And in the demo, in the visualization, we also see different aspects, yeah, different complexes. Yeah, so it's not just for protein.
Okay, that's very helpful. So you mentioned briefly during the demo on the confidence gap, but if you can reiterate again, that'd be great. How does the confidence gap affect your results?
Yeah. So basically, in the prediction, we're predicting the water molecule with different probability. So the confidence cap is the threshold. It filters out anything that's below the threshold. So if your confidence cap is really high, it will only keep the ones with high probability. So there will be fewer number of the final outputs, but those final outputs will have like high probability. So it's mostly useful when you really want to focus on some really high probability ones. But like as you can see in the demo, if some of the water molecules are very evasive, like some cryptic ones, then you probably want to decrease the confidence level so that you can capture most of the water molecule. Then you can look at them and see if those are reasonable for your downstream works. Yeah. So the confidence map cap, what we recommend for most general cases is 0.05. And for those hard ones around the binding pocket, you could try like a zero point 0.5. But it's most of the time you need to tune this based on your downstream task.
Thank you for that sharing. I think that's going to be
Mhm.
very helpful for anyone who's using
Mhm.
SuperWater. So now we have touched for all the amazing things that SuperWater deliver.
Mhm.
Um, but I also want to go on having a different approach. What do you think is the biggest limitation for medicinal chemists using SuperWater?
Mm. Yeah. So first, our input to the training or the water molecule is represented as just oxygen. So it doesn't have the hydrogen. So that means it lacks the dipole orientation and also the hydrogen bound directionality. So if you want to exclusively model this hydrogen bound direction, yeah, you need to be aware that you need to add the hydrogen first, use some other software to optimize the hydrogen position. Yeah, and that's the biggest limitation.
So another question, I think it's also a very important question is how would you validate SuperWater prediction experimentally?
Yeah. So basically, the ground truth for the water position is the PDB structure we have, right? So we can compare our prediction with the PDB ground truth. But the caveat is even the PDB structure, they are not like in a physiological condition. You know, the temperature they use usually is very low. It's not the same as the human body temperature. And also for the crystallography, they have this crystal stacking effect. So some water may be packed together. So it's definitely different than the water position in the actual solvent. So that's some caveat, even though we can compare this to the structure, crystallized structure, but be aware that this may be a bit different than the actual physiological environment. So yeah, but that means we can validate it with the structure. Yeah.
Okay, yeah, I think that's very important. Then I guess maybe something more practical, more closely to the maybe the work of people that some of the audience listening. Well, if you use SuperWater for ligand bound structure, what would be the workflow that you recommend to get meaningful results?
You mean like a workflow for a meaningful result or?
Yeah, if you use SuperWater for ligand bound structure, what would you recommend with the workflow? Would be the workflow to get meaningful results? How would you try the model? What would be the first thing that you should test?
Yeah, yeah. So for example, if for drug discovery, as we mentioned, most of the time you want to kick out those unhappy water. Those unhappy water, and usually they should be like they are like very unstable. They want to go out. So this SuperWater gives you a snapshot of the water position with the probability, but it doesn't show you the dynamics. So the workflow should be like you use SuperWater to give some initial water position, then run some MD simulation to see where the water molecule could go after like some time frame. Then you can see some water may fly away. They don't like to stay in the position. Then some other water molecules they are more fixed. They try to stay there. So you may want to keep those water molecule because they are already happy where they are. You don't want to kick them away, right? So the workflow basically is you use the simple water to give some initial position and you run some MD simulation to see which molecules are more mobile and which molecules are very important, very fixed, and you don't want to touch those.
Thank you for your answer. It's super helpful. So I guess the second last question that I have on the list is, what are some of the mistakes to avoid when using super water in practice that you have seen?
Okay, yeah. One thing is I mentioned first, don't assume the hydrogen there. So there is no hydrogen coordinates. So if you want to, yeah, have a very precise hydrogen bound, you need to calculate hydrogen bound directionality first. Yeah, and also don't assume one confidence cap will work for all. Yeah, based on your different scenario, you need to play with those parameter to see which one could be the best.
Okay. Uh, so the last but not least question would be, would it be possible to predict or, clarify how water molecule affect the protein stability during sustained protein release? For example, like a couple of months long.
Yeah. So as I mentioned, so SuperWater basically is to predict a snapshot. So it's not for the dynamic ones. So yeah, so 6 months is also a very long time. So yeah, it doesn't directly give you that output, but however, it can give you some like early stage screen, serve as an early stage screening tool. So you can use the silver water and also the MD, you can see whether the protein is inherently prone to water-induced instability. Basically, if you in your predicted model you see the water is inside of the hydrophobic core, then it will be very likely it's going to be very unstable because the hydrophobic core they don't want water. But if you have find some predicted water inside, it may be the very bad sign. So it may just break down, unfold very easily. So yeah, so it doesn't directly give you a dynamic, but it could be used as some screening tool.
Yeah, I'm sure it's after this, some of the audience would go and try the model, and perhaps from there we'll see the result. So now I think we have time for two more questions for the audience. If you have any questions, please feel free to open the mic to ask Elaine. Okay, so if you have any questions after this, feel free to drop us or Lane's.
Hi, I have a
Oh yeah, go
question.
ahead. Oh yeah, go ahead.
Yeah, so hi, Dr. Liu. Great talk. I had a doubt. So the model predicts like water positions, and it essentially gives us the affinity of the protein to water, right?
Not the affinity, more like just the position of the water.
Okay,
In
position of water around the protein. But this protein has to be like a complete protein, right? We can't use this in can we use this model for uh, predicted structures instead of only those in the PDB? And because we know that like water actually stabilizes the protein model. So if suppose there's a structure which cannot be like which cannot exist but is actually a predicted model, is a predicted structure by suppose AlphaFold or any other predicted model, wouldn't this give us like a false positive for for that particular protein structure to exist? So we will, to avoid this, we might have to only use like validated protein structures, right?
The predicted protein structure is also acceptable. Yeah, actually, in the workflow, a lot of time we use BOS, we use AlphaFold to generate those structure first, because those structures, they are also trained to be very accurate. So they have all these ratios close to the reality. And our model is also, they actually learns in the realistic ratio where the water should be. So yeah, in the workflow, we actually use those predicted structure as well. Yeah. Yeah.
Got it. Thank you.
Yeah, you're welcome.
Okay, so any other questions from the audience?
Hello, Dr. Liu. Really great and inspiring talk.
Thanks.
So it is not, the question is like, I am a budding computational biologist. I'm getting my master's in applied AI. So I work closely with foundation models and VLMs to develop a new method or a benchmark the current generation of language models and its capability to predict the protein structures and how to evaluate its capability towards the precision medications. So you have any suggestions or advice, like where I want to focus? Like the host asked you about the limitations, and you did told addressed us by we have to optimize the way to find out the hydrogen bonding, right? So you have any other suggestions that where we could do something so that we get a better model?
Okay, let me try to understand the question. Basically, you are trying to use some language-based model, the foundation model, and trying to do
Yes.
the structural prediction, right?
Yeah, specifically
Yeah.
VLMs, like vision language models.
Yeah, I will feel like the biggest limitation will comes in how do you really perceive the environment? Because in the structure, a lot of time you need to know the coordinates, you need to know the relative spatial positions. So for the model to really know what's going on in the input, right? But a language model, from my understanding, it lacks that ability. So that's why we have language model and like image model and more model. So just compare language model with image model. Image model
Hmm.
knows where the pixels are, right? But language model does not know. Does that kind of
Yes.
you can
Uh,
kind of see the difference, right? Mhm.
yes.
Yeah,
Uh,
so I'm thinking maybe have some ways of inputting the coordinates will help improve the results, but I'm not exactly sure how you want to do that because if you just input the coordinates as a text,
mhm.
that's probably not the best way. Maybe combine it with some graph neural network or something else, yeah, to help it understand the coordinates, understand their relative positions better.
Yeah, that answered my doubts. Thank you so much. Really appreciate it.
Yeah, no problem.
Oh, okay. So thank you, for our audience, for the great questions. So if you have any additional questions, please feel free to drop us or Dr. Liu an email, and I'm sure great conversation will follow. So thank you, Lynch, for addressing these questions. And as we wrap up, I want to sincerely thank Dr. Lynch Liu for sharing his expertise and walk us through the SuperWater model and also the demo. And thank you all for joining and engaging in today's discussion. Now, this webinar is part of AI4Life Innovation Talks series, where we spotlight frontier AI tools that help you, the researcher, drive discovery forward. Well, we hope that you can explore SuperWater model on Vector platform without, this is without any coding setup, and continue the conversation within the AI for Life community. We look forward to seeing you at the next AI for Life Innovation Talk session. Until then, Until then, thank you again for your time and participation, and have a wonderful day. Thank you, everyone.
Thank you.
Thank you. Bye-bye.
Not the affinity, more like just the position of the water.
Okay, position of water around the protein. But this protein has to be like a complete protein, right? We can't use this in can we use this model for uh, predicted structures instead of only those in the PDB? And because we know that like water actually stabilizes the protein model. So if suppose there's a structure which cannot be like which cannot exist but is actually a predicted model, is a predicted structure by suppose AlphaFold or any other predicted model, wouldn't this give us like a false positive for for that particular protein structure to exist? So we will, to avoid this, we might have to only use like validated protein structures, right?
The predicted protein structure is also acceptable. Yeah, actually, in the workflow, a lot of time we use BOS, we use AlphaFold to generate those structure first, because those structures they are also trained to be very accurate, so they have all these ratios close to the reality. And our model is also they actually learns in the realistic ratio where the water should be. So yeah, in the workflow, we actually use those predicted structure
Oh,
as
okay.
well. Yeah, yeah,
Got it. Thank you.
yeah. You're welcome.
Okay, so any other questions from the audience?
Hello, Dr. Liu. Really great and inspiring talk.
Thanks.
Uh, so it is not, the question is like, I am a budding computational biologist. I'm getting my master's in applied AI. So I work closely with foundation models and VLMs to develop a new method or benchmark the current generation of language models and its capability to predict the protein structures and how to evaluate its capability towards the precision medications. So you have any suggestions or advice, like where I want to focus? Like the host asked you about the limitations, and you did told addressed us by we have to optimize the way to find out the hydrogen bonding, right? So you have any other suggestions that where we could do something so that we get a better model?
Okay, let me try to understand the question. Basically, you are trying to use some language-based model, the a foundation model, and trying to do
Yes.
the structural prediction, right?
Yeah, specifically
Yeah.
VLMs, like vision language models.
Yeah, I will feel like the biggest limitation will comes in how do you really perceive the environment? Because in the structure, a lot of time you need to know the coordinates, you need to know the relative spatial positions. So for the model to really know what's going on in the input, right? But a language model, from my understanding, it lacks that ability. So that's why we have language model and like image model and more model. So just compare language model with image model. Image model
Hmm.
knows where the pixels are, right? But language model does not know. Does that kind of
Yes.
you can kind of see the difference, right? Mhm.
Yes.
Yeah,
Uh,
so I'm thinking maybe have some ways of inputting the coordinates will help improve the results, but I'm not exactly sure how you want to do that because if you just input the coordinates as a text,
mhm.
that's probably not the best way. Maybe combine it with some graph neural network or something else, yeah, to help it understand the coordinates, understand their relative positions better.
Yeah, that answered my doubts. Thank you so much. Really appreciate it.
Yeah, no problem.
Oh, okay. So thank you for our audience for the great questions. So if you have any additional questions, please feel free to drop us our Dr. Liu an email, and I'm sure great conversation will follow. So thank you, Lynch, for addressing these questions. And as we wrap up, I want to sincerely thank Dr. Lynch Liu for sharing his expertise and walk us through the SuperWater model and also the demo. And thank you all for joining and engaging in today's discussion. Now, this webinar is part of AI4Life Innovation Talks series, where we spotlight frontier AI tools that help you, the researcher, drive discovery forward. Well, we hope that you can explore SuperWater model on Vectra platform without, this is without any coding setup, and continue the conversation within the AI for Life community. We look forward to seeing you at the next AI for Life Innovation Talk session. Until then, thank you again for your time and participation, and have a wonderful day. Thank you, everyone.
Thank you.
Thank you. Bye-bye.
Not the affinity, more like just the position of the water.
Okay,
Yeah,
position of water around the protein. But this protein has to be like a complete protein, right? We can't use this in can we use this model for uh, predicted structures instead of only those in the PDB? And because we know that like water actually stabilizes the protein model. So